Welcome back to the analysis of PDEs. So we'll carry on our discussion over studying the long-term behavior of this kind of evolution equation, where we are particularly interested in the evolution equation where A is some linear or some nonlinear operator satisfying certain conditions, and F is some forcing factor depending on U and T, and U naught is some initial condition chosen from some suitable space actually. So we are interested. So what we have been doing is that we have been developing some of the abstract results to study the long-term behavior of such kind of evolution equations, and we studied also some of the concrete examples. So we studied this kind of problems particularly in the category 1, so-called category 1, that in the first category of the problem we studied that when the initial condition in the nonlinear evolution equation is a fixed condition actually, then what would be the long-term behavior. So in particular, when this long-term behavior, when this flow or the solutions to the evolution equations are gradient flows, then we proved that if your initial conditions are fixed, the long-term behavior of the solutions of such evolution equation is going to be that they are going to converge to one of the stationary solutions of the same equations as t goes to infinity. Okay, so this is something that we have covered already extensively. So now what we would like to move towards what you call the second category of the problems. In other words, saying that instead of taking a fixed condition, we take a bounded set of initial conditions actually, or we take a bounded set, okay, in the appropriate space of initial conditions, that in that bounded set the initial condition may vary actually, so it could be anything. And we are interested in that, okay, if you take the initial conditions from, if you allow initial conditions to vary in a bounded set, then what would be the behavior of the solutions of such kind of evolution equation in long run actually. And it turns out that when you allow the initial conditions to stay in a bounded set, then these solutions, or the solution of the evolution equation, will in long run stay in a ball of certain radius actually. Okay, so in particular, you know, after a long time, the solutions of the evolution equation will stay in a particular set, or it will be attracted by a set actually, and hence we are interested in studying those global attractors of the solution actually. Okay, so the solutions will be attracted by so-called global attractors. I will define in a moment that what do you mean by, you know, attraction, and what do you mean by attracting a solution or attracting a set actually. So we'll talk about it, but essentially we want to study the category 2 type problems, and we expect that in long run the solutions of such kind of initial evolution equation, when you allow your initial conditions to vary in bounded set, is going to they are going to stay in a specific kind of a set actually, which I'll call the global attractors. So what I'm going to do now, I'm going to talk about in the first steps some of the basic theory of the global attractors. I'll talk about the definition, intuition of the global attractor. I'll talk about some remarks about it. Then I'll define the absorbing sets, which is an essential ingredient for existence of the global attractors. And then I'll prove basically a theorem which is going to provide us a sufficient condition for the existence of the global attractors of the solution of nonlinear evolution equation. And after that I'll talk about a concrete example by applying this theory, that okay, we will consider that our favorite reaction diffusion equation, and we will try to study that for that reaction diffusion equation there is a global attractor actually. Its solutions admits they live in a global attractor actually. So this is what that we will like to do. So let's just start with the global attractor. Let me first give you an intuitive picture. Okay, this is not really a tactical picture. This is just an intuitive picture actually. Okay, that will kind of allow you to keep the definition of attractor in your head actually. So imagine H is a complete metric space, and imagine you have some subset in H actually. So let's call this subset A actually. Okay. And imagine this A has a neighborhood, okay? So I don't know that it has some open set actually, which is a neighborhood actually. Then we will say that this subset A of the complete metric space is an attractor of the neighborhood U, of this neighborhood U, if you take any you take a point from this neighborhood and consider the trajectories of, say, the solutions of nonlinear evolution equation that starts from this point. Then these trajectories can go anywhere in this space, okay? But after a long time, they will be always sucked up, or they will always converge in the set A actually. So no matter what initial point, initial condition you take from the open neighborhood, the trajectories that starts from this initial condition will always end up and converge in the set A actually. Then I'm going to say that if this happens, then A is an attractor of this open set U actually. So that's what really is a basic definition of attractor actually. So let's try to put it in a more concrete setting. So here's the definition towards putting the definition in the. So let H be a metric space. Let H be a complete metric space. It could be a Hilbert space, it could be a Banach space, it could be a complete metric space. Then F of T is semigroup actually, is a C0 semigroup. Be a C0 semigroup. Okay? On H. And let A be a subset of the complete metric space H that satisfies following properties. Number one, that this A is invariant under S of T. In other words, that if you take the trajectories of, say, the solutions of nonlinear evolution equation starting from some point in A, okay, starting from some point in A will end up in A actually. Okay, will end up in A. So the A is invariant actually. Okay, that is A is invariant under ST. The second condition, that A possesses, okay, A possesses an open neighborhood, and for A there is an open neighborhood, say U, such that for any initial condition from U, okay, as T goes to infinity, the distance between the trajectory that starts from the initial condition U0 and A goes to 0, okay, as T goes to infinity. So in other words, the trajectory of that starting from U0 from a point in U converges in A actually as T goes to infinity. Okay, And I hope you remember that what is the meaning of a distance between point and a set. So the distance between this explicitly, this distance can be written as that this is the infimum of the distances between S of t u naught and A, where A are the points from A actually. Okay, so this is what really is the definition of this distance. So if A has these two properties, that A is invariant under the semigroup and A possesses an open neighborhood such that any trajectory of the solution of evolution equation, say starting from I'm always going to interpret in the term things in the notions in the terms of the solutions of evolution equation, because this is something of our particular interest actually. Okay, so for any initial condition u naught from the open neighborhood of A, the distance between the distance between the trajectory that starts from u naught, okay, and the set A will go to 0 in long run as t goes to infinity. Okay, so if A has these two properties, then I'm gonna say that A attracts u. Okay, and A, or you can say A is an attractor for u actually. Okay, so it's an attractor of attractor actually. So an attractor is invariant under the semigroup, and it must have an open set, okay, u, such that the trajectories starting from u will end up converging in long run in A actually. Okay, then I'm going to say that A is attractor or A attracts u. Okay, so this is what the definition, the basic definition of the attractor is actually. Here are some little remarks on the definition. So I hope that this definition kind of makes sense with this picture actually that I have drawn actually. Though this is not an exact picture, but you can keep this picture to keep the definition in your head actually. Okay. So here are the little remarks. Okay, some remarks. So A can have many such open sets which are attracted by A. Okay, so it's not necessary that this open set, this open neighborhood of A must be unique. So you can have many such open sets. Now the biggest open set of all these open set, okay, the maximal open set which is attracted by A, we're going to call that maximal open set as the basin of attraction of the attractor A actually. So let me write it precisely, that if A is attractor and U is then maximal open set. Okay. Maximal open set U satisfying condition 2 of the definition, you call that maximum open set or open neighborhood as the basin of attraction. Okay, so it's the basin of attraction. Okay, so that's the first remark. The second remark is that we can also say when A is an attractor, then A attracts open set U, or A attracts the points of U actually. Okay, A attracts the points of the U. Okay, So it makes sense actually. Secondly, so if a subset, if there is a subset B of U, open neighborhood, that satisfies this, that the distance of the trajectories is starting from B. So S of TB means what? It's the collection of all trajectories that starts from B and A, okay, which can be explicitly written as that it is the supremum of infimums, okay, of say X from ST of B and say Y from A of the distances between X and Y's. So if you have a subset of U such that all trajectories that the distance between all trajectories that starts from the set B and A, and this distance is defined in this manner, goes to 0 as t goes to infinity, So in other words, for all points of A, the distance, in other words, all points of the set B are uniformly attracted by the attractor A actually, okay. So like if this happens for an entire set B, then I'm going to say that all points of B are uniformly attracted by A if this distance goes to 0 as t goes to infinity. So if this happens, let me write it. If this happens, then A attracts, we can say that A attracts B uniformly. Okay, so it uniformly attracts B. So this is another important remark. Now let me throw the definition of the global attractor. Global attractor. So what do you mean by that? So if with the same notation, H being complete metric space, S of T being the semigroup, okay. So if A is a compact attractor, it's an attractor that is a compact set as well, topologically. So it's an attractor satisfying the definition, condition 1 and 2, and it's also a compact set. And A attracts all bounded subsets of H. Okay. Subsets of H, then A will be a global attractor. So what do you mean by a global attractor? So it's an attractor that is compact and it attracts all bounded subsets of the complete metric space H actually. Then we're going to call this as the global attractor. Okay? So this is what is another important. By the way, all these notions are the notions from the theory of dynamical systems actually. So the theory of dynamical system is a vast theory in itself actually. So we are not covering in detail the theory of dynamical system, but we are studying really those notions from the dynamical system which are of our interest actually. Okay, so that's the definition of the global attractor. Now let me define another important notion which will play a a crucial role in proving the existence of the global attractor for a given evolution equation actually. Okay? And that notion is absorbing set actually. Absorbing set. So the next definition is about absorbing set. Then I'll talk about the relationship between the absorbing set and the global attractor. In fact, we will prove a theorem in which we will say that if you have an absorbing set, okay, and some additional simple conditions are satisfied, then you have the global attractor actually. So existence of absorbing set is really going to imply the existence of the global attractor. Okay. So what's an absorbing set? So suppose you have a subset of B naught, that is a subset of H, and U be an open set. So it's an open set containing B naught. Okay, so it's an open set containing B naught. If for any bounded set B in U, which is a subset of U, there exists an instant depending on the bounded set B such that after this instant, all trajectories that start from B, okay, will end up in B naught actually. Okay, will end up in B naught. So then we're gonna say that B naught is absorbing in U actually. Okay, so it's absorbing set. So if this is true, then B naught is absorbing, okay, set in U. You also call it that B naught absorbs the bounded sets in U actually. Okay, so B naught absorbs the bounded sets. B naught absorbs the bounded sets in U. So if I make a picture, so imagine this is my complete metric space, and imagine I have an open set in it, and imagine I have a subset of this open set. So let's call this B naught. Okay. Now this B naught is such kind of subset of open set U that if you take any bounded set in U, okay, any bounded set in U, and consider the trajectories, okay, that starts from these bounded set, or you can say that for each such bounded set there exists an instant, or there will be a time actually, that any trajectory that start from the bounded set will end up being in B naught actually, but after this instant T1, and it will always stay in B naught. Okay, so it will always stay after this instant T1 actually. Okay, so for every bounded set, you take say another bounded set, there must be an instant, okay, say T2, such that any trajectory that starts from this bounded set after the time T2 will always end up in the set B naught actually. Then we're going to say that this B naught is really an absorbing set for all bounded sets in U, or B0 is an absorbing set in U actually. Okay, so it's an absorbing set in U. So I hope this definition makes sense of it, makes sense for you actually. Now, what we would like to show, let me give a little remark that existence of global attractor. So if you have a global attractor, implies the existence of absorbing set actually. Of absorbing set. So in other words, if you have a global attractor that attracts the all bounded sets, what you call in the complete metric space, then there must be an absorbing set actually. Okay, and here is the sketch really of the proof, and then we will prove the crucial and the main theorem of our discussion actually. Now, existence of, I must say, bounded absorbing set actually. Okay. So now consider an epsilon. Now let's fix an epsilon and consider the V epsilon. Okay, where the V epsilon is really the epsilon neighborhood for the global attractor A. Okay, so V epsilon is the epsilon neighborhood for the global attractor A. So what do you mean by that? That V epsilon is the union, okay, of the all open balls that are centered at the points in A and have the radius epsilon. Okay, so it's the union of all such, what do you call, open balls. So take A, take all points of A, and on each such point draw the ball of the radius epsilon. Okay, and then put put all these balls in a union. So this would be really the epsilon, what do you call, neighborhood of the set A actually. And my claim is that this V epsilon is basically a bounded, is in bounded absorbing set actually. It's in bounded absorbing set. Why it's an absorbing set? So in order to show the absorbing set, we need to show that, you know, for any bounded set, okay, for bounded sets, there exists an instant that after this instant, the trajectories that starts from that bounded set will end up in the absorbing set, which is V epsilon in this case. So this is what that we would like to show. By the way, since we know that the global attractor A exists, so this means for any bounded set, okay, for any bounded set B in H, we have what? We have that